Okay, guys, we're going to look at, in this problem, we're going to look at example 1258. Okay, this is still erratic motion. It says here, the jet-powered boat starts from rest at s equals 0 and travels along a straight line with speed described by the graph. Okay, so speed described by the graph. Okay, let's look at the graph. Velocity time. It's a velocity time curve, and it's got these two sections here. This is erratic motion again, and from 0 to 25 seconds, it's got this description of the velocity, and from 25 to 50, it's got this. So this is a cubic function. V is a function of t, the t is cubed, and here we've got v as a function of time, but it's a linear function and it's got a negative slope. All right? So the question is, construct the st and at graph for the time interval 0 to 50. Okay, so let's jump right into this. Here is the curve. Okay, so again, we are looking for, they first asked for the st graph. Okay, so if we've got a velocity time function, how do we get our position time function? Just maybe try to answer that yourself quickly. How do I get that? But by the way, guys, at any point when we're doing these problems, I highly encourage you to pause the video, try it yourself, and then see how I solve it, okay? There's so much more value in active learning instead of just passively watching these videos or passively attending a lecture, okay? So even you can try this yourself before I even tackle anything else. Try this problem yourself, or try it in stages as we go through the problem, okay? So, so we've got v and t, so we have v as a function of time. We want s as a function of time, right? We have v as a function of time, we want s as a function of time. So what are we going to do to relate velocity, time, and position? Well, we're going to use this one, right? v equals ds dt, that's our fundamental equation. So if we want position from velocity, we know we need to integrate this equation, okay? If it's a vt curve, okay? If it's a vt curve, if velocity is a function of time, we have to integrate this equation to get our position time. So that's what we're going to do. But first we need to, what's the next step, guys? What's the next step? Or even the second step, the next step. It's to define the region. Okay, so between t equals 25 seconds and 0, we've got v is 4.8, 10 to the minus 3 t cubed. Right? Very, very nice and easy. Okay, then we know we're looking for our position as a function of time. So let's take this. Okay, so v is ds dt. And what is v equal to during this time period? It's equal to exactly this, 4.8, 10 to the minus 3 t cubed. So now we need to separate variables and we need to integrate. Separate variables and then integrate. All right, so we have t on this side, so the dt needs to go over to that side. Perhaps I should write a bit bigger. The integral of ds is the integral of 4.8, 10 to the minus 3 t cubed dt. Okay, then what do we put here? We're starting from 0, so we're working with time. So these have to be time limits. Okay, so the one thing I want to just quickly discuss is that many of you in class would say, well, what are my limits here? Oh, it's 0 to 25. And I say, but that is 100% correct. But what we're looking for is we're looking for a function. Please pick this up. We're looking for position as a function of time, okay? And once we have that function, then we can plug in our known time values to get a position, okay? So you'll see what I mean. So don't put 25 there. Put t, okay? Because we want position as a function of time. And then what about our s? We're just going to have between 0 and s, all right? So on the left here, this becomes s, On the right, this becomes 4.8, 10 to the minus 3, t to the 4 over 4. Okay, and because it's between t and 0, that just stays like that. And this then becomes 1.2, 10 to the minus 3, t to the 4. Excellent. We've now got our function. We've got our function, s as a function of time. Oops, sorry. I need to check the screen. Okay, so now we've got our s as a function of time. We had v as a function of time. We now have our s as a function of time. Very good. So this is always my first step, is get the function. Then the second minor step would be, okay, now I've got my function. What is s at a specific time period, at 25? What is s at t equals 25 seconds? S is equal to, I take that 25, I plug it into there, and I get 468.75. All right, so step 1, guys, function. Step 2, then you plug in any information you want. 25 seconds goes into there. I find my S equals 468. And that's important. This is important because we have a erratic motion or piecewise function. And when we integrate, we're looking for our limits, right? Our limits. It's important that I find that S equals 468 because it forms the limit, the beginning, the initial limit in my new integral, as you'll see. Okay, so that's good there. Let's now look between 50 and 25 seconds. Let's see what's happening there. Well, what is our velocity? What's our velocity equation? Minus 3t plus 150. So our velocity, so again, v is ds dt, and our velocity is minus 3t plus 150. So this is a function of time. So again, we have ds is minus 3t plus 150 dt. We separate variables. Now, what are my limits here? Well, this now forms my initial position during the second time period. So I have to put 468.75 there, and s, because again, I want s as a function of time. And this equals, now what are my limits here? Well, that would be 25 and t. Don't put 50 there initially. Don't put 50. I know you want to do it. I know you want to do it. Don't do it. Okay? So this becomes then on the left, s minus 468.75. And on the right, we have minus 3t squared over 2 plus 150t. And this is between t and 25. T and 25. Okay, so you can go do this whole integral. This ends up being s equals minus 3 over 2 t squared plus 150t minus 2343.75. Okay, now I've got my second function. This is in meters. Excellent, I've got the second function. Then I can say, okay, what is my S? What is my position at t equals 50 seconds? My position then, we need to just plug that in there. If we quickly do that, minus 1.5 times 50 squared plus 150 times 50 equals minus 2343.75 gives us, and please check me on this one, 1406.25 meters. Okay, so we are ready now to draw the graph. We found our functions, right? And we found the values at the extreme points of those functions, okay? So let us let us draw this graph. Okay, so we started off with velocity. Okay, this was our VT curve. Now we can draw our ST curve. So by the way, this here was it had a T-curved shape, T to the power of 3. If you integrate this, you're going to, over this time again, you're going, there has to be something to the power of T to the 4, right? Because we're integrating. So the function here is S equals 1.2 10 to the minus 3 T to the 4. And then, I didn't draw this so nicely. I was a bit silly there, but the second function, so we just drew the first function there. The second function begins, remember, at this point. That's where it begins, and we then draw it from that position. We draw this function, and it looks like this. Okay, I know it's not super accurate, but that is it, and this is minus 3 over 2 t squared plus 150t minus 2343.75. Okay, so there we have it, and that's 50 seconds, that's 25, and we know that S here was 468.75, and S there is 1406.25. Okay, so I think that's good. In the next one, I will draw the acceleration time curve. Cheers.